Hello and welcome to today's video. In today's video, we are going to discuss what we call crystal field theory. Crystal field theory. So let's quickly dive into it. What is this theory all about? So crystal field theory is a theory that explains how the ligand or the arrangement of ligands around a central metal ion, which is usually a transition metal, affects the energy of the metal's d orbital. Now, to simplify this, the crystal field theory usually just talks about the interaction. So it focuses on the interaction of the ligands and the metal ion. Now, this interaction gives us more information about how the energy of the metal in terms of the d orbital is affected by this interaction. All this is happening in what we call coordination complexes. So when we have a coordination complex, remember, we have a metal which is at the center, then this metal gets to interact with the ligands. Remember, the ligands will donate a pair of electrons, and that interaction results in what is known as dative bonding or coordinate bonding. Now, when we are looking at what is known as when we're looking at what is referred to as a normal metal ion. A normal metal ion contains what we call degenerate orbitals. So by degenerate, it means that all the orbitals have equal energy. Now, we are looking at the d orbitals in coordination complexes. So it's the d orbitals that interact with the ligands. So when we're looking at a normal metal ion, in terms of energy, in a normal atom, we have what we call degenerate energy. Remember, d orbitals, we have 5 of these d orbitals. To name them, we have the dxy, the dxz, the dyz, dx squared y squared, then the dz squared. So all of these, when we're looking at a normal atom, they tend to share an equal amount of energy, and that is referred to as degenerate orbitals. Now, what happens when these normal metal, the orbitals in the normal metal ion interact with the ligands? So the golden question is, what happens to the d orbitals in a normal metal ion when they interact with ligands? That's a very important question that we have to understand. So when these orbitals begin to interact with the ligands, what happens is there is a repulsion. The interaction of ligands and d orbitals results in a repulsion on some orbitals. That is, some orbitals in the d orbital, because we're looking at the d orbital. So basically, what happens when there is that interaction, some of the orbitals, which we're going to mention very quickly, they experience a very strong repulsion. So there is a strong repulsion on some of the orbitals, and then for others there's a weak repulsion. So when you experience a very strong repulsion, it means that you're going to occupy a higher energy level. Then when you experience a weak repulsion, you occupy a lower energy level. Now, which of those four orbitals will experience a higher energy? And I'm going to give more information as to why it happens like that. So here we have the dx squared y squared and the dz squared. So all these together are known as the EG set. So these experience a very high or a very strong repulsion, and therefore they, upon splitting, they tend to occupy a higher energy level compared to the dxy, the dxz, and the dzy. So these together are known as the T2G set of orbitals. So these will occupy a lower energy level because of the weak repulsion, and these other ones will occupy a higher energy level because of a strong repulsion. So this is a very important question that we have to ask ourselves and understand. Now, why are we going to experience what we have just explained? Why is it that some orbitals will occupy a certain higher level of energy, and then the other ones will occupy a lower energy level? So this has got everything to do with the orientation. So the repulsion is affected by the orientation of the orbitals along or on the axis. So this repulsion is as a result of the orientation. So when we look at those ones that will experience, let me say, a strong repulsion. So here we're referring to the dx squared y squared, and then we're referring to the dz squared. When we look at the orientation of these, obviously we're looking at the z, y, x plane. So for this particular orbital, you find that these are found along the axis. So according to this theory, these tend to experience a very high repulsion because ligands also interact with them in that particular orientation. So the ligands will interact with the electrons of the d orbital along that particular axis. So because of that interaction, there is an electron repulsion which enables these guys to occupy a higher energy level. This also happens to the Z. So when we look at the orientation of the Z, so this is Y, this is X, this is Z. So the Z is found along the Z axis. So again, in that axis, the ligands interact with that particular orbital. So what happens there is an electron repulsion, which results into these two orbitals occupying a higher energy level because of that particular electron to electron repulsion. Remember, ligands also come with a pair of electrons. So because of that, electron density results into a repulsion, and therefore the splitting will favor these two orbitals to be found on the higher side in terms of energy, and the other two will be found on the lower side. So when we're looking at it from a splitting, so in terms of energy splitting or energy distribution, we're looking at two scenarios here, and I'm gonna give more details about this because we have what we call a weak field and we have what we call a strong field, but I'm gonna give more information about this. But generally what we are talking about is, if we're looking at the energy levels, if this is our energy level, so those 5 orbitals at some point they are degenerate. So they have equal energy when they say degenerate. Then after splitting, so we are considering an octahedral. So after splitting, we are saying we're going to have 2 orbitals there, which is the dx squared y squared and the dz squared. Then the other three, which is the dxy, the dxz, the dyz or zy, will be found down below. And we're saying these are called the EG, then these are known as the T2G. So there is this splitting. So this splitting is what is referred to as the crystal field splitting, that is in an octahedral represented by a delta, then delta O.